今天还是要点名，虽然下大雨，是不是？所以呢，还是请你的同学呢，因为今天要颁奖哦，这样人看起来有点稀疏，是不是？所以呢，要点名，所以要请你的同学呢，还是麻烦你赖一下，跟你同学讲一下，请他们过来，好不好？哦，我想可能有些同学还卡在路中间呐，不过呢，我想今天东西都有带吧？好 ，OK， 好的。Okay, let's get started. So, let's recall what we have learned in last week. On Monday. And this is important. I hope you still remember. In order to read how, in order to understand this triangle diagram, it's very important that to understand this is ABS system for liquid-liquid traction. And I just want to work with you one more time to understand how to get this, how to understand these figures. So, you know, this is the example we explained to you on last lecture. And, you know, to specify that the weight fraction of the axion is 0.525 in the MIBK ridge phase, fix both the phase and the composition of the water ridge phase. So actually, this is a kind of mixture. This is kind of mixture. And you have two phases. And one phase, which is MIBK ridge phase, contains 25% acetone. So once you know that this MIBK ridge phase, and you have 25% acetone. Acetone is here. So when you read this, you start to read this acetone here, which is 25. 25 is here. So once you know that there are two phases, which is, one is MIBK ridge phase. So this line should go to this part. So that's why we know that this 25, and then this need to go to this part. So this is the MIBK ridge phase. Please remember this because this might be in your final exam paper. So, and then now, you know that there are two phases. For example, one of these two here. So MIBK ridge phase, this is the point you need to find out what's the composition in this phase. So there are two phases. One is MIBK ridge phase, one is water ridge phase. So, and then the only one information you know is 25% acetone, right? So once you know there are 25% acetone, so please tell me what's the percentage of the water in the MIBK ridge phase? Can you tell me that in this place? So MIBK ridge phase, we know that acetone is 25%. How about water? Water is here, right? Water is here. So you point here, that will be 5. That will be 5. So 5% water, 25% 25% MIBK. So, and then what's the percentage of the MIBK? 70, right? 70. So in this case, you know there are 5% water, 25% acetone, and 70% MIBK. And you put 5, 25, 70 together, that will be 100. Right? That will be 100. So this is the one phase. How about this is how about the water ridge phase? The water ridge phase is that you follow this tight line. You follow this tight line here and go to the water ridge phase here. So you follow the tight line and then go to the water ridge phase. So this is the point you need to find out the composition of the water, acetone, and the MIBK. So please tell me what's the percentage of the water here? There will be about 82, something like this, right? This 80, this 85. So it will be about 82, right? 82 water. Okay? And what's the percentage of acetone? Acetone is somewhere around here, right? If you go to this acetone, that will be, well, 16, right? It's above, just a little bit above 15. So that will be 16 acetone, right? So you have 20, 82, 16, and then, of course, MIBK will be what? MIBK will be 2, right? MIBK is here. So you follow this line here is less than 5. So that means that is 2 here. So, you know, this liquid-liquid attraction, we know the water phase, water-rich phase is 28% water, 16% acetone, and 2% MIBK. And MIBK rich phase at 5% water, 25% acetone, and then 70% MIBK. Okay? Okay. And this is the example which we just discussed with you on last lecture. And please practice this by yourself. One more time, I say to you, please practice this by yourself. Okay? And then at the last lecture, we also talk about the adsorption. I hope you remember the adsorption. And adsorption, important thing is that this example tells us that you have carbon tetrachloride. And carbon tetrachloride here, you want to remove the carbon tetrachloride by adsorption process. So in order to remove carbon tetrachloride away from this room, or in this gas phase, you need to put activated carbon in this space, in this room, and then carbon tetrachloride will be adsorbed on the activated carbon. So you remove carbon tetrachloride away from this in the air. Okay, and this is a question you want to know. And the important thing is that you need to know that there's one which is called Langmuir equation. And I will give you the Langmuir equation like this, and you need to know the constant A and the constant KL. And P is partial pressure, right? P is partial pressure. Okay, so please practice this by yourself. So I hope you will get very good score in your final exam. Okay, so today we are going to talk about chapter 7, which is energy and energy balances. And energy balances is that, again, is, you know, as long as you remember the general balance equation, the general balance equation apply to energy balance, apply to mass balance, apply. So this is important, okay? So I'm sure energy is very important, right? And very expensive now, okay? You cannot use 发电, right? Okay, you have to use technology to generate energy, okay? So energy can be provided by free energy like sun, wind, tides, or energy can apply from the hydroelectrical power like waterfall or dam, like something like this. And this is wind power, right? And this is the dam, okay? Hydroelectrical power. And also you can burn the fuels like gas, oil, or solid fuels, okay? And even you can use nuclear power to generate energy, okay? And this is an important issue in Taiwan at this moment. But anyway, this is out of the scope in our topic, in our lecture here. But the first one is energy balances. The washing the energy lead to reduce the profit, right? So if you waste energy, you lose money. If you can use energy efficiently, you make profit, right? So as an engineer designing a process, one of your principal job would be the counts carefully for the energy that flow in and flow out of each process unit, and then determine the overall energy required for the process. So it's very important, you know, energy in and energy out, and how much energy you consume, right? because energy cannot, and if you waste a lot of energy, you lose money. So for the energy balances, how many power is required to, for example, how many power is required to pump 1,250 cubic meter per hour of the water from a storage vessel to a process unit? So this is one of the questions. If you want to pump this amount of the water and per hour, and how many energies you need? Okay, this is one of the questions. And another question might be how much energy is required to convert 2,000 kilograms of water at 30 Celsius and then make it become 180 Celsius. This is another energy question for you to know that you need to calculate how much energy required. And then energy will convert to the money, right? So a highly exothermic chemical reaction like A to B take place in a continuous process reactor. If 75% conversion of A, the conversion rate is high, then this is a good reaction, right? The 75% conversion of A is to be achieved at what rate must energy be transferred from a reactor to keep a content at a constant temperature? This is another question. Okay, it's all related to energy. And then if you burn the coal, must be burned each day to produce enough energy to generate the steams to run the turbine. This is a power generator or the power station to generate electricity, to produce enough electricity to meet a daily power requirements of the city of the 500,000 people. Okay, this is another question for you. Okay, but let's start from the very beginning about the energy. So we need to know the forms of the energy. And first of all, we need to understand the first law of the thermodynamics. You will learn this when you are in the third grade in the college here. But here, you are just a freshman. I just tell you the very simple way to express the first law of the thermodynamics. So thermodynamic system is not related to time. So thermodynamic always tell you it's nothing with the time. So it tell you the very beginning stage and the final stage. Okay, you want to know when the time reach to the thermal equilibrium, and we are thinking what kind of situation we will have. So this is called thermodynamics. Okay, the thermodynamic system is the material and the radiative contents of the microscope values in space that can be adequately described by thermodynamic states, variables such as temperature, entropy, internal energy, and pressure. But here, important thing is that you need to understand what is this. So thermodynamic system is always enclosed by wall. This is walls, or we call boundary. So we can call wall boundary. So once you want to think of a thermodynamic problem, you always think you need to have a boundary first. Okay, and you only think of the boundary inside the boundary. Okay, let separate it from its surrounding. This out of this boundary is called surroundings, or we can call it environment. Okay, this constrain the system. So now you understand we have a system inside the boundary, and we have surroundings outside the boundary. So the boundary, or sometimes we call walls. So this is one of the example. I hope you still remember we have a piston here. The piston, and we have a cylinder. And the piston will go in or come out will move downward or move upward to the from this piston, or from this container. So if we think of this as a kind of thermodynamic state or condition, inside is called system. This is inside here is called system, and this is called boundary, and outside of this is called surroundings. Okay, so let's take a look of the definition of the boundaries. So the boundary, a wall, restrict passage across it by some forms of matters or energy, making the connection indirect. Sometimes a wall is not more than an imaginary two-dimensional closed surface through which the connection is the surroundings is direct. So this can be imaginary, it can be real, but you can just imagine this is the surrounding. Okay, this is the system. So what's the surrounding? The surroundings is the reminders of this universe that lies outside the boundaries of the system. It is also known as the environment and the reservoirs. Depends on the type of the system, it may interact with the system by exchanging mass, energy, including heat and work. Okay, and the momentum, electrical charge, and some conserved properties. So this system and surroundings can have exchange of what? Mass, energy. So energy can be thermal energy, right? So we call this heat. Okay, it can move. So this is kinetic energy. Okay, so not only kinetic energy, thermal energy, but also kind of mass energy or what? Momentum, or electrical charge, or some kind other properties. So let's take a look of the energy first. The total energy of a system, including these three parts. The first part is called kinetic energy. So the kinetic energy, I'm sure you all know this kinetic energy. The translation kinetic energy is that the energy due to the translation motion of the systems as a whole relative to the some frames of the reference. Okay, we only deal with the translation kinetic energy in this text. So this ball move around, move from A position to B position. This can be called kinetic energy. However, in this text, we don't talk about rotation kinetic energy. I mean that this baseball can rotate, right? But here we don't discuss about rotation kinetic energy. Okay. How about potential energy? The potential energy, the energy due to the position of the system in the potential field. So like gravitational or electrical magnetic field. Okay, it can be also applied this kind of field, different fields. Okay, in the text, we will deal only with the gravitational potential energy. So this ball, if it's on the first floor, the potential energy is low. If this ball is in the second floor, third floor, the potential energy is high, right? Okay, so the third one is called internal energy. What is internal energy? It's simple. All the energies passes by a system other than kinetic or potential energy. Neither kinetic energy nor potential energy will be called internal energy. Okay, easy, right? However, we want to talk about a little bit more detail about internal energy. So, as you can see, this is a ball. If you throw a ball from the ground to the sky, for example, you understand here the kinetic energy is very high because you throw a ball from the ground, right? And when you reach the highest position, and the potential of this ball is high, is the highest, and it drop. Okay, so energy due to the motion of the molecule. So this is the kinetic and the potential energy. However, when we think of this baseball itself, there's something inside. Okay, so energy due to the motion of the molecule inside this ball relative to the center of the mass of the system. Okay, so the molecule in this ball will move. Okay, energy is due to rotational and vibrational motions of the and the electrical magnetic interactions of the molecules. So next next year you will learn something like atomic vibration. So the molecule here in this ball, it won't stay as it is. It will move. Sometimes it will vibrate. Okay, so this is called internal energy. Unless the temperature go to 0 Kelvin, everything stop. So there's no internal energy. Energy stop. Okay, so energy is due to motion and the interaction of the atoms and the subatomic constituent of the molecule. This is called internal energy. However, you are an engineer. Normally, we don't consider internal energy at this moment, in this stage. We only think of potential energy and the kinetic energy. However, if we take a look inside this ball, we will consider internal energy. Okay. So there's two terms which are very important in the energy. It's called heat and work. Heat related to the energy, thermal energy. If you have temperature, then you will have energy. And work means that it's a form of the energy. Okay. Suppose a process system is closed. This system is closed. So the closed system is that no mass is transferred close to the boundary. So this system is closed, and the mass then cannot go out and come in. Okay, while the process is taking place, so energy may be transferred between such a system and the surroundings within two ways. So no mass transfer, but however, energy can be transferred. So important thing here is no mass was transferred, but energy may be transferred. And energy, if the mass cannot go out, what happened? Why the energy can be transferred? By two ways. The first way is heat. The temperature will change, right? So the thermal energy will be delivered from the system or from the surroundings. So as a heat, the energy that flows as a result of the temperature differences between the system and the surroundings. The direction of the flow is always from a higher temperature to a lower one. Okay? So the temperature will flow from the high temperature to the low temperature. So molecule will change, will move. The energy will move. How about the work? So the energy that flow in response to any driving force other than the temperature differences, such as the force, torque, or voltage. So apart from the temperature differences, the driving force can be force, can be torque, or can be voltage, electrical voltage. Okay, this is one of the example for here. Please read this by yourself. Okay, this can be moved in, can be pushed in and come out, the piston. So heat and work are two different ways of the transferring energies from one system to another. So this is a system, and energy move to the surroundings. Surroundings can be another system too. Okay. Right. So the units of the work is that, the energy is equal to the force times the distance. So you know that the force we can be in Newton, right? Times meter. This will be called joule. This is SI system, right? The dyne times centimeter will be ergs. And this is what? This is CGS system. And this is American engineering system, feet times pound force. American engineering system, right? So this is the unit of the energy. And you notice when you are in the first year, when you study this in the chapter 2. However, you might see some of the unit called kcal or car or calorie. Actually, it's calorie, okay, or BTU. BTU is British thermal unit. British is United Kingdom, right? British. Okay, so these are the another definition of the energy, but it's also, when you see this, you will say, wow, this is the unit of the energy. Okay, this is not unit of the force or this is not unit of length or time. Okay, this is kilocalorie or calorie or BTU. So what's the definition of this? This is a very special, this is a special definition. Among the heat that must be transferred to a specified mass of the water. Remember, this is the unit definition is water. To rise the temperature of water by a specified temperature interval at a constant pressure of the 1 atm. So what happened? At the 1 atm, the water temperature increased from 15 to 16 of the 1 kilograms of the water. And this is called kilocalorie. However, if increase 1 degree from 15 Celsius to 16 Celsius and only 1 gram, this is called calorie. If you increase the temperature 1 Fahrenheit using of the 1 pound mass, and this is called BTU. Actually, you don't need to remember exactly the definition, but you just know that, wow, I learned there are different type of the unit of the works of the work. CGS, SI system, CGS system, American Engineering System, and this is the special definition. By increasing the water for 1 degree, can be Celsius, can be Fahrenheit. Okay, by 1 kilogram, by 1 gram, or by 1 pound mass. Okay, right. So thermodynamics is a very important for chemical engineers, and also it somehow is also very it can be very difficult. Okay, you need to use your imagination to understand some of the concepts. Okay, so thermodynamics is a branch of the physics concerned with the heat and the temperature and their relationship to the energy and the works. So thermodynamics is related to energy always. So there are 4 laws of the thermodynamics. You need to remember this very well. Okay? Thermodynamics, 0 laws of thermodynamics. What is 0 laws of thermodynamics? The 0 laws of thermodynamics is that if 2 systems are each in thermal equilibrium with the third one, they are also in a thermally equilibrium with each other. What does that mean? If I have 2 systems, and these 2 systems, this one is thermal equilibrium with the third one, and this one is the second one is thermal equilibrium with the third one. So the first one and second one will also be the thermal equilibrium to each other. Easy, right? Okay, this is like mathematics. Okay, so this is 0 laws of thermodynamics. Easy. The first law of the thermodynamics is what we learn from of this lecture and in this course, is the internal energy of the isolated system is constant. That means what? Conservation of energy, input equal to output. So if the internal energy is not constant, then that will be a different story. But however, for the first law of the thermodynamics, the condition is that internal energy of the isolated system is constant, then we had to follow the conservation of the energy. That means input equal to output. Okay? How about the second law of the thermodynamics? The second law of thermodynamics is heat cannot spontaneously flow from a colder location to a hotter location. It makes sense, right? Because you know that this is against the nature. If the heat flow from a cold location to a hotter location, this is against the nature. Okay? How about the third law of the thermodynamics? A system approaches absolutely zero. All the processes cease and the entropy of the system approach to a minimum value. What does that mean? Absolutely zero means that it's 0 Kelvin. Everything stops, even molecular, even atoms stop to move. So the energy becomes the lowest volume, minimum volume. That's why you can do the travel, you can do the time travel, right? Because if I froze you to become 0 Kelvin, everything stopped. It's like you slept. And then 30 years later, we make the temperature higher. They let you become, let you be alive. Okay, so you can move 30 years later. You can wake up in 30 years later. Okay. So the first law, now we want to know the first law of the thermodynamics. It's also called the law of the conservation of energy. This is what you need to learn in this lecture, okay, which states that the energy can neither be created nor destroyed. So energy cannot be created or destroyed. So when we think of the general balance equation, accumulation equal to input plus generation minus output minus consumption. According to this general balance equation, applied to the energy balance. So, and then for the first law of thermodynamics tell us that the energy cannot be created or nor destroyed. That means what? You don't have the term of the generation and consumption, right? So as a result, the general balance equation can be simplified as accumulation equal to input minus output. That's easy. So to be exact, you can say the rate of the accumulation. What does that mean, rate? Because when we talk about continuous process, we need to also think of the time, right? So the rate is of the accumulation of the energy in the system will be equal to what? The rate at which the energy, including kinetic energy, potential energy, internal energy, is carried into a system by input. Okay? And what this is the first term here. The second term, output, is that the rate at which the transfer out of the system by output streams. It can be also kinetic, potential, and internal. However, you have to add one more terms, which include heat and work, because these two are also the important terms for the energy. Okay, so you need to consider heat and work in the mass balance. In the energy balance. So the energy becomes the accumulation equal to input minus output. So this is a drinking bird. Please, if you go to YouTube and type drinking bird. Drinking bird is a great way to see the first and the second laws of the thermodynamics in action. Okay, this bird will keep on drinking water. Okay, because this follow the first law and second law. Of course, it cannot drink forever. Okay, it cannot drink forever. Just take a look of these in the YouTube. Right, so let's move to the section 7.2, kinetic and potential energy. So, for the kinetic energy, you know that E sub K stands for kinetic, right? Equal to half of the mass times the velocity power 2, right? So you understand this kinetic energy, this M is the mass, object of the mass, and this is velocity. You know that? So in the fluid, so this is what we learn in the high school. However, as a chemical engineer, we need to know the continuous process. So the E sub K over dot means what? It's divided by time, right? Okay, so it's continuous process equal to the, of course, the half. This is the mass flow. And this is mass flow. And then this is the velocity too. Okay, so you can change this equation become like this. Okay, no problem. So I have a question for you, which is example 7.2-2. So the kinetic energy transports by a flowing streams. So if I have a pipe, the pipe, and I let the water flow into the pipe and come out to the pipe. So the water flow into a process unit through a 2 centimeter. ID stands for inner diameter. Inner diameter means this pipe, the inner diameter is 2 centimeter at a rate of the 2.00 meter a cubic meter per hour. So the water will flow in, which is 2 cubic meter per hour, and come out, of course, 2 cubic meter per hour, right? And I want you to calculate the kinetic energy for these streams in joule per second. Can you do that for me? Joule per second means what? This is SI system. SI system. Okay, so once you know this, and then you will know that, well, Professor told me when we want to use the continuous process and for the energy transfer, kinetic energy transfer, this is the equation we want to use. Okay, so what do you have here? We have, first one, you have the transfer. This is called volumetric flow rate. Volumetric flow rate means 2.00 cubic meter per hour. And then this is mass flow rate. Anybody want to tell me how do you transfer volumetric flow rate to the mass flow rate? Can anybody tell me? 0.5 point. This is your final chance. Yes. Huh? Thank you. Density, right? Density. Good. You are very fast. Very good. Okay, so once you want to convert volumetric flow rate to mass flow rate, this is density. Now, what's the density of water? 1, right? That's easy. Okay, how about this? V, velocity. Velocity is what? So once you change the volumetric flow rate to the mass flow rate, this is easy by density, right? How about volumetric flow rate to, this is called linear velocity. Linear velocity means that what? This is volumetric flow rate means the cubic meter per hour, right? Per time. And linear velocity means what? Meter per hour, right? So what can you do? Can you transfer cubic meter per hour to the meter per hour? Yes, you can, because you know the diameter. You know the diameter of the pipe, right? So you just pi r square, right? You just divide this by pi r square, and you can get the linear velocity. So as a result, you will know the kinetic energy, how much kinetic energy is required for this process. Okay? I don't want to waste your time to do the calculation for yours with you. Please go home and do some practice by yourself. Okay? Okay, the final is gravitational potential. Gravitational potential is that E sub P, P stands for potential, right? Gravitational potential is equal to mass times gravity times what? The height. Okay? So again, if you want to do the mass, you want to do the continuous process, the potential will be what? E sub P over dot equal to M over dot G Z. Again, this is the important things for you as a chemical engineer to understand this equation. So every time when you want to see the energy transfer or energy change, so this is the equation you need to use. No problem, it's easy. Just divide it by time only. Okay? So this is one of example 7.2-2, potential energy increasing of the flow of flowing fluids. So the crude oil is pumped at a rate of the 15 kilogram per second from a point of 220 meters below the Earth's surface to a point of 20 meters above the ground level. So the crude oil will pump from under the ground, right, and pump it out, and we want to, and then it go up to 20 meters above the ground level. And I want you to know how much potential energy is required for this process. Easy. So you just use this equation. And this Z2 is what? Z2 is 20, right? Minus what? Z1. Z1 is what? It's minus 20, 220. So total is what? Total is 240. The height differences is 240. And you know the mass flow rate. You know the gravitational units. Bingo. You got the answer. Okay? This is easy. Right, ladies and gentlemen, I really want to introduce you 7.3, section 7.3, but unfortunately, I run out of my time. This is the last lecture today, and we have something to do after this, so I will stop here. Right, I really want to tell you this. Okay, I'm sorry that this is important. Please, this might be in your final exam, okay? This is important. There are three systems. One is called open system. One is called closed system. One is called isolated system. It's all related with the mass and the energy. So, for the open system, is that the mass, you can regard this is open system. You have a glass of water. The glass of water is, the water is open to the space. Okay? So the mass can be transferred from the glass to the air. So mass can be opened. Mass can be transferred in and out. Energy also can be transferred in and out. This is called open system. However, so this is the open system. The energy and water and mass can be transferred in or out to the system. Okay, and for the closed system, it's like, you have a bottle of water, but you have a stopper. You have a stopper in the top of this bottle. So the mass cannot come out. However, the energy can come out. Why? Because you have a bottle of a beer, for example, and you take it out from the refrigerator. It's cold, very cold. And eventually the beer the temperature will increase because of what? The energy will release from the beer, right? So the energy will come out. This is called closed system. However, if you have an isolated system, that means what? You have an isolated bottle of water, which is vacuum between the containers. So the energy cannot come out. The mass cannot come out as well as the energy. So you can keep the temperature inside these vacuum bottles very well. So this is called isolated system. So as you can see here, the surroundings and system, there's nothing exchange, neither energy nor mass or the metals. Okay? So this is closed system, open system, closed system, and isolated system. And this might be in your final exam paper. Okay? 好。